So we looked at ionic bonding, which was between a metal and a nonmetal. Now we'll look at covalent bonding. Covalent bonds are formed from a shared pair of electrons between two atoms, and this occurs with nonmetals. So covalent bonds are formed between nonmetals. For example, water, there are two covalent bonds in water right there. Water is called a molecule because it's a group of atoms that are united by covalent bonds. So molecules are united by covalent bonds, and these have to be nonmetals. There's different ways we can describe the composition of molecules. We can use the molecular formula, which is the actual formula. For example, glucose is C6H12O6. That's the actual formula for glucose. I can reduce that formula to give me the empirical, which is the simplest ratio, CH2O. So the empirical is just the reduced form. It doesn't tell me what glucose is, but it is the reduced form. We can also use the structural formula. For example, hydrogen peroxide H2O2. Structural formula just shows which atoms are bonded to each other, like this. So structural just kind of uses dashes to indicate which atoms are bonded together. Properties of molecules: they have a low melting point. They do not conduct electricity. They're brittle, and they tend to be gases or liquids at room temp. They're exactly opposite properties of ionic substances. So molecules, nonmetal compounds, have these four properties in common with each other. One of the big ideas with molecules and covalent bonds is writing Lewis structures. I've given you 4 rules here that I follow whenever I write Lewis structures. First of all, number 1, the least electronegative element is in the middle. And so when you look at the periodic table, the element that is farthest from F is in the middle because F is the most electronegative. Hydrogen is always on the outside because hydrogen only wants 2 electrons. It's always on the outside of the structure. I always work from the outside in, and that's because the central elements can have less or more than 8 electrons. But the outside elements have to have 8. So I work from the outside in. Let me give you a couple examples. I'll do pH3 first. When you're drawing the structure, first thing you need to get are the order of atoms. P is going to be in the middle because hydrogen cannot be in the middle. And so when we write the Lewis structure for pH3, that's what we have. Hydrogen has 1 valence electron. I'll use circles for hydrogen's valence electron. And phosphorus has 5 valence electrons because it's in group 5. Well, 1's got to go to each hydrogen so they can share those. And then you've got 2 more left over. We'll just put at the top of P. Now, in the correct Lewis structure, hydrogen should have 2 shared, and each hydrogen has 2. And then if you count the ones around P, P has 8. So it has the octet of electrons as well. So everything's happy, and they have the octet of electrons. So that's the correct Lewis structure for pH3. Let's do a couple more. Do SCl2. Least electronegative is in the middle, so that means sulfur is in the middle. Chlorine's on the outside. Work from the outside in. Do your Cl's. Sulfur is in group 6, so it has 6 valence, 1 here, 1 here. And that's going to give each chlorine 8. I've got 4 more left over on sulfur, and I'll just kind of put them on either side of the sulfur. And if you count up the number of electrons around the Cl's and the S, you'll see that there are 8. And these are shared pairs of electrons now between sulfur and chlorine. And I like to use different symbols. I'm using X's and circles. You can use dots, you can use squares, you can use whatever. I like to use the different symbols to indicate where the electrons come from. But they're all valence electrons. Let's do one more. N2. It's only got 2 atoms. Just randomly put the 5 electrons around each nitrogen like this. Now if I try a single bond that is 2 electrons, which I've tried here first, it doesn't work because each nitrogen only has 6. They want 8. So I can't add electrons, but I can try a double bond or a triple bond. I'll try a double bond first. I'm going to move electrons right there. So I'm going to move those electrons, and here's what it looks like now that I've moved the electrons. it has given this nitrogen over here 8 valence electrons with that double bond. However, the first nitrogen still has 6. So that doesn't work. What I'm going to do is try triple bond. So this was a double bond here. I'm going to try triple. Move those electrons into the bond, and here's what I get. So a triple bond is 6 shared electrons, but if you look, each nitrogen now has 8 valence electrons. So they have the octet, and that's what they want. So they're happy now with the 8 valence electrons. So we have a triple bond. With Lewis structures, I always try a single bond. If that doesn't work, try a double, then try a triple. But with Lewis structures, quite honestly, it's a lot of trial and error, and it takes just a lot of practice in order to get these correct. When we're showing multiple bonds, we can use dashes. So for example, the SCl2, which I drew before, we can actually use dashes to indicate a single bond. But you can only do this after you've done the Lewis structure with the dots first. So there's a single bond. A double bond would be 2 dashes, like CO2 forms 2 double bonds. But again, you have to do the dots before you know that there are double bonds formed. And then a triple bond, we just did nitrogen. That actually forms a triple bond, which would be 3 dashes. So you can use dashes, but only after you've done the Lewis structure first to determine the number of electrons shared. Exceptions to the octet rule. Atoms with less than an octet. Number 1 here, BF3 is an example of less than an octet. Now, the exceptions occur around the central atom. So the outside atoms, like F, they're going to have 8. So I'm going to start with the F's and work my way towards the middle. But F has to have 8 because it's a terminal atom. It's on the outside. Boron is in group 3. It has 3 valence electrons. 1 there, there, and there. Now, in this structure, the F's have 8, which is good, but the central atom B only has 6. And boron is one of the few that have less than 8, and it is okay with less than an 8. So boron, one of the few exceptions with less than 8. Sometimes you can have more than an octet. Noble gases like xenon will form more than an octet, and the reason is because noble gases already have 8 valence electrons. So let me draw you the structure for XeF2 here. Xenon has 8. One's got to go to each fluorine to give fluorine 8. But then I've got 6 more left over that are just lone pairs around the xenon. So around the xenon there's actually 10 valence electrons. That's okay because the central atom can have more than an octet. There are many exceptions with more than an octet. I can't give you every exception there, but if the exception occurs, it occurs on the central atom. It does not occur on the outside atoms. It is possible to have an odd number of electrons, usually with nitrogen, but I am not going to give you any that have an odd number of electrons. So the 2 exceptions that you're going to watch out for are less than an octet or more than an octet, but they have to occur only on the central element. Covalent bond types. Covalent bonds are not always shared equally. We're going to use electronegativity, which is going to tell us which atom wants the electrons more. But the shared electrons are more strongly attracted to the atom that is more electronegative. So the atom that is closer to F is where the electrons are attracted to. First type of covalent bond is a polar bond. This is formed when one atom is significantly more electronegative than the other. Polar bonds, anytime you have 2 different nonmetals, it will be a polar bond. Anytime you have 2 different nonmetals bonded together, it's polar. Let me give you an example. We've already done SCl2, so I'll do it again. SCl2. When we do this Lewis structure, the electrons that are shared are not shared equally. So these electrons here and here are not shared equally. The atom that is more electronegative, in this case the Cl, gains a slight negative charge. So we'll say Cl is S minus, slightly negative, because it hogs these electrons here. So both chlorines kind of hog those shared electrons. So sulfur doesn't get an equal share of those electrons. And then sulfur becomes slightly positive. So slightly negative means more electronegative. So your most electronegative element gets a slightly negative charge, and that would be a polar bond in this case. Nonpolar bonds are bonds in which both atoms exert an approximately equal pull on the electrons, and this only occurs between elements, between compounds of the same element. So for example, F2, since it's F bonded to itself, they have the same electronegativity. So these electrons right here, they're shared equally because there's no electronegativity difference. It's a nonpolar bond. The only time you get a nonpolar bond is if it's a compound of the same element. There are 4 different types of bonds: ionic, polar covalent, nonpolar covalent, and metallic. We're not going to get into metallic, so we're going to worry about the first 3: ionic, polar, nonpolar. So how do you know if it's nonpolar, moderately polar, very polar, or ionic? You need to know this chart right here. Let me give you an example. SF6. Without drawing all of the dots. SF6. Fluorine has a value of 4.0. Sulfur has an electronegativity value of 2.5. Now, those values come from the book. I don't expect you to know the values. I will give them to you. But if fluorine has a value of 4, sulfur has an electronegativity value of 2.5, the difference, obviously, between 4 and 2.5 is 1.5. So the difference in electronegativities is 1.5. That means the bonds between sulfur and fluorine are very polar. So they're shared electrons, but fluorine takes on a slightly negative charge and sulfur takes on a slightly positive charge. But that would be a very, very polar bond based on this chart over here. And again, I want you to know those numbers. Let's say I have barium and chlorine, BaCl2. Barium has an electronegativity value of 0.9. Chlorine is 3.0. And again, those numbers you don't have to know. I will give them to you. But the difference is 2.1, which means this bond is ionic. And with ionic bonds, we don't share electrons. We give electrons away, or we gain electrons. In this case, barium has 2 valence electrons, but it's not going to share electrons with chlorine. It's going to give its valence electrons to chlorine. Now, chlorine will get 8. Barium is going to lose 2, so it will have 8 as well. In an ionic bond, it's a transfer of electrons. You gain and lose electrons. Only in a covalent bond are you sharing electrons. So only in covalent bonds will we draw Lewis structures. So again, know the charts. Don't worry about the actual values for electronegativity because I will give those to you.